Hello everyone, and welcome back to another video. My name is Jamil, and today we're going to be going through another lead code problem. Thank you so much for tuning in. If you continue tuning in so far, I hope you've been learning from the questions. Today we're going to be taking a look at another company's problem, and it might seem a little bit tricky to begin with, but there is a simple method of us approaching this problem and thinking about the problem and then solving it. I did use the hints for this problem, so I'm going to be using the technique, I guess, that LeetCode suggests to us, and from what I've seen in my previous solution, it looks to be like a fairly straightforward solution, simple and easy on memory and runtime. So, without further ado, let's take a look at the problem. So today's problem is titled minimum bit flips to convert a number. Okay, it's an easy problem. You will probably see this with companies. So a bit flip is of a number x is choosing a bit in the binary representation of x and flipping it from either 0 to 1 or from 1 to 0. Okay, so if you're familiar with binaries, binaries are made up of zeros and ones, and so what we are trying to determine is if we have to go from the number, for example, 10 to the number 7 and represent it in its binary representation, how many steps do we have to take in order to get there? So for example, 7 is the binary representation of 111. And if you're unfamiliar with binary, I need you to know that when you're reading binary, you should be reading from right to left, okay? And it goes from like a base value of 2. So this first one will be like the 0th index. So since it's a 1, that means we can take into account 2 to the 0, which represents the number 1. Since this number is the number 1, it's 2 to the 1, which is now 1 plus 2, which it gives us 3. And then this is 2 to the 2, which is 4. So 1 plus 2 plus 4 gives us 7. Okay? So you start reading from the right to the left, and you do 2 to the 0, 2 to the 1, 2 to the 2, and these are exponents. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. And every time you see a 1, you're adding, and if every time you see a 0, you're not. So, and for example, for x is equal to 7, the binary representation is 111, and we may choose any bit, including any leading zeros not shown, and flip it. So we can flip the first bit from the right to get 1, 1, and 0, right? The second bit from the right to get 1, 0, and 1, and then flip the fifth bit from the right, a leading 0, to be 1, 0, 1, 1, and 1. So if we count for every number 1 here, we have 2 to the 0, which is 1, 2 to the 1, which is 2, 2 to the 4, 2 to the 2, which is 4, and then 2 to the 3, but that's represented by a 0, so we're not even going to take that into account. And then 2 to the 4, and 2 to the 4 is what? 2 squared is 4, 8, 16. Okay, right? So basically, like, you just keep on adding and adding and adding every time you see a 1. That's how you get to your goal number with binary. I know this is a little bit of a loose explanation of what binary is, but that's not the point of the question. If you have any like trouble understanding binary and how binary works in coding problems, I would suggest maybe taking a look at a couple of videos, understanding how binary works, so that this question can be a little bit more clear to you. All right, so we're given 2 integers, a start integer and a goal integer, and we need to find the minimum number of bit flips to convert from start to goal. Okay, so we're going to be passed 2 parameters, right? We are passed 2 arguments, and both arguments are going to be valid integers, okay? Because if they aren't valid integers, then we won't be able to translate them into their binary representation. We are required to get their binary representations, right, of each the start and the goal number, and then determine how many binary flips will it take to represent the second number from the first. Okay? And there is going to be a method that we can use built into JavaScript that will help us get there. And so what are we returning? Return the total number of flips you need to do. Okay? And so that being said, if you have any leading zeros, then like these don't take into account, like they don't change your answer at all. Leading zeros mean that they are binary representations that are not currently active, right? So they are switched off, which is what the 0 represents. In order for me to show you what or how I got to the solution, allow me to introduce you to bitwise XOR. It is a function that is built into JavaScript. So the bitwise XOR operator returns a 1 in each bit position for which the corresponding bits of either but not both operands are 1. Okay, so what does that mean? Because that is not very clear. Let's take a look at this specific example on the MDN, right? We have the letter A representing the number 5 and the letter B representing the number 3. And as explained to you previously, if we're reading binary, we read from right to left, right? So 1, 0, and 1, that's 2 to the 0, which is 1, 2 to the 1, but we're not taking it into account, and then 2 to the 2, which is 4, right? So 1 plus 4 is equal to 5. Same thing with B. 2 to the 0, which is 1, and then 2 to the 1, which is 2, and 1 plus 2 is equal to 3. Now, what bitwise XOR does is it takes the binary, the bit representation and the binary representation of each number and then compares them to each other. Every index that is the same, so if it's 1 and 1, let me just make this a little bigger. If it is 1 and 1, they are the same representation. So 2 to the 0 here and 2 to the 0 are both lit up technically, right? Since they are represented by 1, and since they are the same, bitwise XOR, which is represented by this little hat, I guess is what you can call it, that you would see on top of like special characters in different languages, it would return a 0. But if you take a look at the second number here, when you're taking a look at the representation of 5, it comes back with 0. And when you take a look at the representation of 3, it comes back with a 1. And since 0 or 1 are two different numbers, right, it will return 1 in your bitwise XOR, right, in your bitwise XOR comparison. And the same thing with the third representation. So 1 and 0 comes back with 1. Okay, so now that we have that in mind, let me go back to the solution. So I need to have an answer to iterate over. And the reason why I'm going to do that is because in order for me to go from a binary representation of 5 to the binary representation of 3, I need to switch this 0 and this 1, right? To make it so that it is represented by 1, 1, and 0 instead of 1, 0, and 1. So if we have a comparison and we know that we need to make a change, and every time we need to make a change, the bitwise XOR will return with a number of 1, all we need to do is count, once we have run our comparison, how many 1s show up and return that total number. Okay, so let's see. We're going to do an answer, all right? And I'm going to make it a string. And the reason why I'm going to make it a string is because I need to run bitwise XOR and a bitwise XOR operator on start and compare it to goal, right? But the thing is, if I console log answer, right, and for the sake of the problem, because this is expecting a number up here, I'm going to return the number 1, right? Look at this. I'm also let me just remove this for the time being. I'm going to remove this type just to show people what I am taking a look at. Okay, if I am doing the bitwise XOR representation alone, it returns a number to me, right, of 13. I don't know what that means. It doesn't mean anything to me, right? Like I can't work with this because like I guess what it's reading is that it's saying start to the power of goal actually, you know what, to the power of isn't even represented by the caret pointing upwards, but two asterisks next to each other. So I can't work with this number 13 at all, right? I need to figure out what the bit representation of it is. So we're going to change this to a string. And in order for me to convert the number into a bit representation, I'm going to go to string, and I'm going to put it on base 2. I don't know if you guys were noticing here earlier when I was saying 2 to the 0, 2 to the 1, and 2 to the 2. I was saying like a representation of binary is used on the base of 2, and then the exponentials are basically what you see here. So it's 2 to the 0, 2 to the 1, 2 to the 2. And when we convert it to a string, we're going to be using base 2. But now when I console log answer, take a look at what I see. Right? Look at this. I see 1, 1, 0, and 1. And if we calculate this again, 2 to the 1, which is 1. 2 to the 2 to the 0, sorry, which is 1. 2 to the 2, which is 4. And then 2 to the 3, which is 8. So 8 plus 4 plus 1 gives me 13, right? Which is what it was before. The previous number that we saw being console logged. So this is just the binary representation of the number 13. So now that I have the binary representation of the number 13, I can start working with this. Okay. This is also a string, since we can tell from my assignment up here and my declaration that I have declared it to be a string. And since it is a string, we can iterate over it. So I am going to say let I equal to 0, and it's going to be I is less than answer.length, and then I plus plus, right? So how do we know how many steps we need to do or we need to take in order to change one number to another? As like I mentioned it earlier, but we're going to count the number of ones, right? Because when Zor runs the comparison, when there are two different numbers, differing numbers, it returns with the number of 1, right? So let's take a look at this. If answer of I is equal to the, oh, I need my if statement outside of my brackets, you know, like the professional developer that I am. If answer of I is equal to 1, we are going to, well, what are we going to do? Actually, I forgot to mention this, but we're going to need a counter, right? And it's going to be a number because that is what this function is expecting us to return. It's expecting us to return a number. I'm going to add to my count, right? So when any of these numbers in here are 1, I know that I have had to make a change in order to reach to my desired number, right? So if I was to give you guys a couple of hints here and to tell you what's going on, iterate over the comparison, right? And add to your step counter, which is count up here, right? And add to your step counter to determine the total number of steps required to change the number over to the goal number, to change the start number over to the goal number. Okay. And so we add to our count, and then once we have figured out the total number of steps, we can just return that. And let's see if we do that. If we run our program here, what do we come back with? It comes back with 3, right? If we take a look at our console log, we see that there are 3 1s in there. We had to take 3 steps in order for us to make the change. And if we take a look at our second case, right? Again, it is the number 3. So our start was 4, that was 3, and our goal was the number 4. We ran a comparison of their bits representations, and we came back with 1, 1, and 1. So everything needed to change, right? And since we had 3 1s, that is what we expected to see. We expected to see 3 steps in order for us to change from the from the bit representation of the number 3 to the bit representation of the number 4. Okay. If you want to see what I mean here, I am going to say start to string, and we're going to say 2 here, and goal dot to string, and we're going to say power 2 here. and let's see. Okay, right? So the binary representation of the number 10 is represented by 0, 1, 0, and 1. And the binary representation of the number 7 is represented by 1, 1, and 1, right? 1 plus 2 plus 4, which is 7. And then if you run the comparison, right, we read from right to left in binary. The number 10 starts with 0, but the number 7 starts with 1. And those are immediately two different numbers. We need to change that. Okay, so that's number 1. The second number is 1 here and 1 here. We don't need to do any steps, so that's a 0. The third number is 0 and 1, right? So we need to change that number. But then take a look at this. The binary representation of the number 7 is only 3 digits, whereas the binary representation of the bit representation of the number 10 is 4, right? So we need to add one more number in our solution to represent the number 13. Now, 1, 1, and 1 is the same thing as saying 0, 1, 1, and 1. So again, if you are familiar with binary, 1 represents that the bit representation is switched on, whereas 0 is switched off. So you can add as many zeros as you want to, and it won't change the number to the leading answer, right? Like it can be as many zeros as you want it to be, and it's not going to change your answer, right? Because it only changes your answer if, for example, this 0 was a 1 there. If this 0 was a 1 here, that's a completely different number, right? That's an extremely, extremely large number. But we only care about the 1s and the 0s that affect us, right? So once we submit the solution, it's going to take a little bit longer in order for it to submit. But what I'm going to do is I will take this solution and I will post it online on my GitHub for you to take a look at it, play around with it, see what it's like, and to get familiar with it. But I hope you learned something here today. I hope you learned something about bitwise operations and the XOR operator and what does it do. I hope you learned a little bit about binary and how to approach problems like this. So if you liked the video, please like the video, subscribe to the channel. I would really appreciate that. Leave a comment in the section below and tell me what you thought of the video, what you thought of the question, if you think it was hard, if you learned anything. There is something that you can do here that can improve on this solution. So I will put my improved solution where you can replace this for loop in the GitHub as well, so that you can take a look at that and see if you can come up with it. The hint might be here is that you might want to use the reduce function. Okay. So yeah, if you do end up using the reduce function, how does it improve on your solution? That might be something that you might want to think about. That might be a question that might come up on an interview for you. And I guess it is quite handy to think about ahead of time. But yeah, without further ado, I guess I'll leave you to try that now, and you can take a look at the solution on the GitHub afterwards. Once again, thank you so much for tuning in. My name is Jamil, and I'll see you next video.